Okay, we'll do this one here. We have identified the intervals on which f of x equals quantity x minus 2 to the 2/3 power is increasing or decreasing. Justify your answer. F prime of x, what do we do with this 2/3? 2/3, right? X minus 2 to the negative 1/3. All right, and then with the chain rule, the derivative of the inside, which is 1, so we don't have to adjust anything for that, right? So now what we have is 2 over 3 cube root of x minus 2. And if we set that equal to 0, well, that's never going to be equal to 0, but so we can't find where the derivative is 0, but can we find where the derivative is undefined? Yes, we can, because we can set that denominator equal to 0, can't we?
Yeah.
So if we set our denominator equal to 0, we have, and we divide by 3, square, cube and all that, we have 0 equals x minus 2, so x is equal to, x equal to 2, which is our critical number, but it's a different type of critical number in that it's not 0, but where the denominator is 0. So we go ahead and make our number line, and we put here f prime up above and f below, and then to the left, what do we have?
Negative.
Negative to the left, because it's negative, right? So negative, so the function will be decreasing here. And to the right we have positive.
Positives.
And it'll look like this. And so increasing, so f is increasing on what interval?
2 to...
On 2 to infinity, because f prime is
greater than 0.
greater than 0. F is decreasing on negative infinity to 2 because f prime is less than 0. This is a good type of problem to have on a test, I think.
Oh yeah, that'd be great.
I don't know. I don't know if I have it on a test or we'll put it on a test, but something like that would be pretty good. So, questions on that?
No. When do you think our next test will be?
Okay, that's a good question. We actually may not have a real test until the semester final, but we're gonna review like crazy for it.
Yeah.
So it should be pretty good. We could possibly have a test before that, but the problems, I want to go through the curriculum here. All right, that's a fair question. Next.
I'm nervous.
Next, we go to the note card here, which is first derivative test for local extrema.
Did we talk about this last year? Local extrema.
Yeah, we actually did toward the beginning of the school year. So what you remember, if you talk about local extrema, is from over a year ago that you remember that. So that's good.
And it sounded
Just
very
rang a
clever.
bell. Yeah, we
Yeah.
did. We talked about that very much.
The word extrema really just clicked in my mouth.
Huh? Yeah.
Extrema?
Very
Yeah.
good. Okay, here's the first derivative test used to find where local relative maximum or minimum exists. And then what we do is like the last one, we determine what the intervals, the function is increasing or decreasing. If the function changes from increasing to decreasing at a critical point which exists, that x value is the relative maximum. No. That's not right. Then that y value, that should be y value. You understand why I made that correction?
For number 2, it should be 1.
Yeah, because it's the y value that is the maximum, right?
Mm-hmm.
Now, x value is where that maximum occurs. So I want you just to go ahead and write this. This is a and likewise, the function changes from decrease and increase at a critical point which exists, then that y value is the relative minimum. And then it says to find the relative maximum minimum value, you take that x value and substitute it to get that y max min value. Does that make sense? Now I want to look at this problem that we did most recently here today. This one right here. Okay, doesn't that one apply here? First of all, you have to have a point, a value that exists. Does this function exist at x equals 2? Yeah, it does, right? Because you can plug in 0, you can plug in 2 at that critical number, and you'll have 0 to the 2/3 power, so that checks, check. And then we're changing from, at that critical point, from decreasing to increasing. And so that means that we have a relative minimum. Now, the thing that's really good about drawing this number line is with these arrows, if you can just go ahead and connect these arrows like that, you can actually make a minimum like that. And so it's a graphical representation of it. So when you draw the number line properly, it gives you the answer, it helps you get the answer to that question. So that's another reason that number lines are our friends. Okay, let's go on here. The function defined here for all real numbers has a relative minimum at x equals question mark. So I want you to go ahead and apply your understanding there of note card 26, is it? To do that one. We have some You already finished it? You already finished
Yeah.
it? Is that fast? Is that fast?
Hopefully.
Probably wrong.
You're wrong. Gross and, what did I say, vulgar? What's the I in? What could I say?
Gross and vulgar.
Including nasty. Does that make sense? It's close enough.
Get that one.
So we have to find where it's increasing, decreasing, so.
Okay, Sam, it's the same thing we've been talking about, right? So we go ahead and take this, we're going to have f prime of x, and that's equal to 3x squared minus 6x, is that right?
Gross.
So we have
Atrocious.
0 is equal to 3x
Icky.
times x minus 2. Does that look right?
That's
That's what I got.
So you have x is equal to 0, x is equal to 2. And now we resort to our friend,
The number line.
the number line. And when we put here f prime up above and f below, and so we go ahead and put in here and just figure out a number less than 0. Well, that's going to be a negative negative, is that right? Negative times a negative, so it's going to go like this. And then between 0 and 2, we would have a positive times a negative. Well, excuse me, that's positive there, that's negative there, right? And then greater than 2, we would have this little thing. So where do we have a relative maximum?
0.
So relative maximum at x equals 0, For justification, we go to, what is the justification right here? Because what happens? Because
Function changes from increasing to decreasing.
well, the function changes from increasing to decreasing, but the reason is because f prime of x changes from increasing to decreasing, positive to negative, right? F prime of x changes, f prime of x changes from positive to negative.
But doesn't it change from, it changes from negative?
What was your question?
Nothing, I figured it out.
You figured it out when you asked the question, but still sometimes the best questions are the ones that you hesitate to ask. Okay, but this really should be by now a pretty easy problem, right? Because we've done number line analysis, I hope enough that, and then again, when you do the number line right, it's just, to me, 100% intuitive, okay? If you connect these arrows here, you just have that, you see that maximum right there, and you're good. Okay, let's go ahead to the next one. State need local extrema for this one right here. So go ahead and work that one out, number 2. And I think this one right here was one of the ones we went over last year when we did the pre-calculus parent functions. Not that this is an official pre-calculus parent function, but let's look back at number 1. Yeah, that was right. Okay, what do you think for this one?
I don't really know.
Why don't you know, or what's your hang up here? What is your critical number going to be?
0.
0, right? Okay. What is one of the things about having a relative minimum or maximum? Something that begins with if. If what? If it. What does it say in the note card there? If it. Let's read. I'm going to bring back some bedtime reading here.
It's what turns out I get to go to sleep.
Okay, if. Okay. It says which exists. I was thinking if it exists. So I got my wording wrong. Which exists. So look at number 2. Does that critical point exist?
No.
Does not exist. Okay, what does this function look like? Looks like this. Looks like whoop and whoop. Okay, does not exist. So therefore no local extrema. here you work this out, y prime is equal to, I think, negative 2 over x cubed. Is that right?
Oh,
Yeah. And even now you have a critical number, that critical number is 0, but you tie back into the original and you don't have a point that exists. So you have the qualifications. You're going to have, if you do a number line, you're going to have your critical number at 0, and you're going to have, well, I'll put y prime 0. You have y prime over y, and you're going to be positive here to the left, right? So increasing, and negative to the right. So you have all that. What's the one thing you're missing? The point that exists. So you can't connect these and get a maximum out of it. Okay, next. Absolute extrema on an interval, and here we're bringing into play extreme value theorem, the number 2 of the big 5. What was the number 1 of the big 5?
Was the IDT? No, it was the
Yeah, I think number 1 is, I think it's the mean value theorem.
mean value theorem. That's fine.
Yeah, I think number 1 is the mean. And of course, and what other theorem is related to the mean value theorem? Rolle's theorem. Okay, good job. Okay, and then I'm glad you remember intermediate value theorem, so I'm glad your memory is tickled enough to bring those up, because we got to keep these all going. Okay, so extrema means extreme values, Latin for extremes, and so f of c is the absolute, and absolute is global is another way to say it. Global, I guess you could call it universal too, but convention is global. Okay, global or absolute. And also, well, relative and local. Anyway, if f of c is less than or equal to f of x for all x in the domain, so the very lowest or tied for being the lowest value in that whole interval. And likewise, you have a maximum if f of c, if the output value is greater than or equal to f of x for all x in the domain. And here's the theorem. If f is continuous on a closed interval, and you have to have a closed interval, then f has both an absolute maximum value and an absolute minimum value. So you got to check for continuity within that interval. Do you have to check for differentiability?
Yeah.
No.
No.
No, you don't. Because what happens is you could have a situation like this, where if you had an absolute value function like this over an interval, it would not be differentiable here, yet would have qualify for being an extreme value theorem in that case. So you just have to watch out for that. You got to have your closed intervals for a thing to apply. Now, it's possible if you have an interval just on one side, you could have, you still could have an absolute maximum within the interval. But anyway, here are ones right here. I want you to use this. You should be able to do this one, number 1, with your calculator. Okay, determine whether the extrema may not exist, are located on the endpoints, and are located inside the interval. And what would an endpoint qualify as? Okay, endpoint would qualify at -3, or at 1.5, at x equals 1.5. Those are endpoints, and within the interval is inside that. So I want you to go ahead and use your calculator to draw, and you should be able to figure that out. And so go ahead and do that one, number 1. For number 1, do the maximum and minimum or extrema exist for number 1? Even before you put it in the calculator, does the absolute extrema theorem apply?
Yes.
Why does it apply? Extreme value theorem. Why does it apply? Because what?
It's continuous.
Because continuous over this interval, right? And what else? Closed interval, right? So absolutely has to, they both have to exist, both a maximum and a minimum.
Yeah, I borrowed your calculator.
Let's see here, if I can find one. I know I have one. I think it's going to be right over here. Aha, yes, just where I left it. Okay, this is what I got for this one here. And so the critical numbers I get here are 0. And first of all, I'm going to put the lowest value here, -3, and 0, and then the other end point is 1.5. What about this 9/4? What do we do with 9/4? What do we do with this 9/4, right? Because that's another critical number. What do we do with it? Okay, I'm going to make a more directed question. Is 9/4 going to be part of the domain of this function here?
Yeah.
Really? The domain of the function is between -3 and 1.5. Is 9/4 part of that domain?
No.
No, it's not.
So it's not.
We're not going to use it because that's just not, we're looking at this. And so what you're going to do is you can plug in, you have x, f of x, and these are your candidates. This brings up a new piece of vocabulary today. It's called a candidate test. Okay, the candidates are the endpoints and the critical numbers in between the endpoints. And so now you can plug this in, and to me, 0 is going to be the easiest one because that's going to be 5, right? And then if we plug in -3, what do you get for that? -3 minus negative x to the 4th minus 3x squared. X cubed plus 5. Plus 5. If we go to like zoom 6. So we can see here that that would be a candidate. But then we have this -3 and we have this 1.5, right? So at -3, we have 5, right? At 0, we have 5. And at 1.5, we have, what was that? At 1.5, we have negative 10.19, is that right? Let's just look at the graph again. So we have -5. Is it, yeah, isn't that right? Hang on a second. Or is it 5? 3 we had 5, right? At 3 we had 5. And then we should have this value up here at negative something, right?
So
Something is messed up. I know what it is. Where did I make a mistake? Here's the mistake right here. Okay, it's this thing right here because we have negative 4x minus 9. Well, that sure as heck is going to be, this thing is going to make this thing a negative. So we're going to have, it's going to end up, instead of being 9/4, it's going to be negative 9/4. So negative 9/4 is part of the deal. And we have 0 and 1.5. Okay, let's look at this again. So we have negative 10.19. We have 5, and negative 9/4. Let's go ahead and find that. I'm going to go to 0.25. So negative 9/4 would be right there, 13.543. And then at 1.5, we were, what is it? Negative 10.19, okay. So what are the maximums and minimums? Maximum of what? Minimum of what?
Oh, it has a maximum. Is it that 13.543?
Yeah, so 13.543. And you say where x is equal to negative 9/4, and minimum of negative 10.19, where x equals 1.5. So that is it, ladies and gentlemen. We will see you tomorrow.